See about the TTT diagram. TTT diagram is time temperature transformation. Here in this diagram there will be a particular composition which will not change, but we will be changing the temperature and time thus by finding out at what temperature what happens to the particular composition which is there. So at a definite composition, if you are drawing the plotting a diagram for temperature versus the logarithm of time, then it is called as the TTT curve. The TTT diagram indicates a specific transformation starts and ends, and also it shows what percentage of transformation is happening at a particular temperature. The aim of the TTT diagram is this: it determines the structure and portion in the curve to obtain specific property. So from that curve, you can find out at what portion particular specific property is exhibited by that amount. So it is also called as isothermal transformation diagram. Hence, the TTT transformation curve, that is the TTT curve, corresponds to the start and finish of transformation which extend into the range of temperatures where austenite transforms into pearlite. So here it starts and then it transforms to pearlite. So you can see at a temperature 727 it starts the eutectoid temperature, and from there the transformation starts, and when the austenite is converted into pearlite, the transformation the material is transformed into pearlite. So above 550 degrees centigrade, the austenite transforms completely into a pearlite. Then below 550, both pearlite and bainite are formed. But below 450, you will be having only bainite. The microstructure you can see here how they are. Okay. So at the midpoint, you will be having different structure. And when the time goes on, okay, this is the timeline which is given, the red color line which is the horizontal line, and when the time goes on the microstructure changes. So from austenite you will be having both pearlite and bainite at a temperature of 550, below 550, but below 450 you will be having only bainite structure. Okay, so this line from C to D denotes that a transformation is occurring. So from C to D you can find out that at C you can see that the microstructure is different, and with the time you can maintain the temperature at that above 600 degrees, somewhere here at 620 or something. So at this temperature of 620 you are allowing the material to be like that for a time of 10 seconds or 15 seconds or 10 hours or something like that. Okay, here it is given in seconds. So there is a transformation which is happening. The microstructure itself changes. Okay, so here the microstructure mixes, that is the solid will be melting. Okay, and here it forms the alpha ferrite and Fe3C mixed together. You can write this, I see the pink lines and here. Okay, so that is how the microstructure changes with respect to time. So TTT diagram gives you the information regarding the transformation which is happening in any phase or in any material with respect to time. From this curve, it is the same. You can see same graph is here. You can see that the horizontal line CD that runs between the two curves marks the beginning and end of the isothermal transformations. The dashed line curves represents the time to transform half of the austenite to pearlite. So they indicate the line where half of the austenite will be turned into pearlite. So the complete isothermal transformation diagram of an iron carbon is given here. So you will be having the austenite state. Here B indicates the bainite state, M indicates the martensite, and P indicates the pearlite state. So from austenite, with the time they transform to pearlite. Here at 600 degree, above 600 degree, they remain in the austenite state. But when time goes on towards the right, when it moves, you can see that they become pearlite. Similarly, at the temperature of above 450 degrees, you can see they remain in the austenite state, but when time goes on, they change to bainite state. Okay. And ultimately, when you are cooling it, when you are decreasing the temperature, they come to the martensite site at about the temperature of 220 degrees. So the martensite state starts at 220, then it increases with the reduction of temperature. Okay. So when you are reducing the temperature, you will be getting the martensite which increases. Okay. So this is the representation of the temperature, the diagram which represents the transformation of the temperature and time on any liquid when it is heated or when it is cooled. Okay, so this is also the same diagram which is explained in a different pattern. So here it is austenite is changed to pearlite, and this lines indicates the extension of the solidus line and the liquidus line. Okay, previously we might have studied about the solidus line and the liquidus line. Similarly here, these two blue lines represent the curved blue lines represents the differentiation between different phases. Okay, here to the left of this blue line you will be having entire austenite, and to the right of this blue line you will be having the entire pearlite. So in between you will be having austenite which is mixed with the pearlite. Similarly, at the temperature of 300, you can see that it remains austenite, and when time goes on, it becomes bainite, B letter. Okay. But in between, they remain in the state of austenite plus bainite. But when you reduce the temperature further, they become martensite plus austenite. Completely change of martensite happens at low temperatures. So at low temperatures, the alloy of iron carbon remains in the martensite state. But when you increase the temperature, the phase changes, the phase transformation happens, and the phase transformation which is happening in that material with the temperature and time is called as the TTT diagram. TTT diagram gives us the information regarding the nature and type of transformation, the rate of transformation, the stability of the phases, how they are, whether they are stable or not. Okay. Under the isothermal transformation conditions, the temperature or time required to start or finish the transformation, the qualitative information about size scale of the product, hardness of the transformed products, and what the factors affecting the triple T diagrams are the composition of the mixture, whatever we are adding the components with iron, okay, and the grain size of austenite, they affect the TTT diagram. So the triple T diagram is very important in estimation of the iron carbon alloy. The iron and carbon exist in different forms and at different temperatures with respect to the time. So we should be knowing that at what time and at what temperature a particular mixture or phase will exist, which can be applicable. Okay, so you have to study about the iron carbon phase diagram for the application purpose.